The entire chapter about alcohols, phenols and ethers has already been uploaded as the previous video. In this video, we are going to be talking about the various mechanisms that we come across in the same chapter. So first is the acid catalyzed hydration of alkene, and this is one of the preparation methods of alcohols. So what happens is alkene reaction with water in the presence of an acid leads to the formation of an alcohol, and the addition reaction takes place in such a way that it follows the Markovnikov's rule, which means that the negative part, that is the OH minus, gets attached to the carbon atom having less number of hydrogens. That is what we observe here. Let's discuss the mechanism for this reaction. First step is the protonation of alkene to form carbocation by electrophilic attack by H3O+. In simpler words, it basically means the alkene is going to get attacked by the H3O+, and protonation means a hydrogen atom is going to get added. So basically an alkene is going to get converted to an alkane, right? Or rather the double bond is going to break. I shouldn't say the word alkane, but it's going to get converted to an carbocation. So alkene is getting converted to carbocation. And how is this happening? This is happening by the attack of the H3O plus electrophile, and what happens in the process is protonation. Okay, so the alkene is getting converted to a carbocation. First, the synthesis of the H3O plus. So water reacts with the H plus ions because the acid is present in the solution. You have the formation of the H3O plus electrophile. Electrophile means electron loving. So the alkene is going to react with the H3O plus, and the oxygen atom basically wants to get rid of the hydrogen atom. So this double bond is going to break, and what happens is the H is going to get added to one of the carbon atoms. Now this leads to the formation of the carbocation. So this hydrogen attacked here, and you have the carbocation formed. So an alkene is getting converted to a carbocation by the electrophilic attack by the H3O plus electrophile. Next, what is happening is the water molecule is going to attack as a nucleophile on the carbocation. So here what will happen is the carbocation is undergoing a nucleophilic attack, and that leads to the formation of basically the carbocation, which has the OH2, the water molecule, attached to it. Okay, so here let's take the carbocation. Carbon is having a plus charge, and this carbon has a hydrogen atom. Now this is reacting with H2O. The reason it's acting as a nucleophile is because of the presence of the lone pair of electrons on the oxygen atom. Now what will happen is this lone pair is going to attack this carbon atom. Okay, because the carbon does not have, so carbon is electron deficient, H2O is electron rich. That's why it acts as a nucleophile, and this leads to the formation of this particular product. Okay, now what will happen is this OH2 directly is attached. So obviously one of the hydrogen atoms is lost to make sure that it gets converted back to OH, and oxygen's valency is 2, right? So the last step is deprotonation of the alcohol. Deprotonation to form alcohol. So that particular molecule is undergoing deprotonation, which means loss of hydrogen atom, and so the oxygen atom has a positive charge. Now another water molecule will come in Okay, the lone pair of electrons will attack this, and that will take the hydrogen atom away. And this leads to the formation of a alcohol molecule from an alkene plus H3O plus. So first step, what is happening? We have protonation of the alkene taking place. This leads to the formation of a carbocation. Protonation is taking place by the attack of an electrophile, that is H3O plus. Next, the nucleophile water is attacking the carbocation, and this leads to the formation of the it leads to the basic bond formation between the carbon and the oxygen atom of the water molecule. Then this that is oxygen atom is electron deficient, or rather it has 3 bonds, so it gets a positive charge because its ability is to form only 2 bonds. And what the water molecule is again attacking and making sure that the hydrogen atom is kicked out, and this leads to the formation of an alcohol. Now the reason we said that the mechanism follows the Markovnikov's addition is because of the stability of the carbocation. Now let's take this particular molecule for example. Okay, there are 2 ways that this could have happened, right? The CH3, okay, the bond, this alkene could have broken in 2 ways. One, the positive charge could have been on this atom, or the positive charge could have been on this atom. So here, let's take the first case where your positive charge is on the second carbon atom. Okay, and this next case where the positive charge is on the third carbon atom. That is, I'm just numbering it in random, it's not based on IUPAC, but so this will have a CH2, this will have a CH2 plus. Now the stability of the carbocation increases with the increase in number of alkyl group the carbocation is attached to, and that's why these two are electron releasing in nature. They will stabilize the CH group, whereas in this case the CH2 is getting stabilized only by this ethyl group, whereas this carbon atom is surrounded by 2 methyl groups which are going to stabilize it even more. Now hypothetically speaking, if like we had, let's say this is also bound to different alkyl group, or rather it is bound to 2 other alkyl groups. Okay, so this would have been a straight ether. So here in this case, this would have had lesser number of hydrogen atoms, right? 1, 2, 3, 4, and that is why this particular carbon atom would have gotten a positive charge, and that would have been more stable than this one. So more is the number of alkyl groups, more is the stability of carbocation, and that's why we are saying the acid catalyzed hydration of an alkene is followed by the Markovnikov's addition. With that, we're done with the reaction of alkene on reaction with water in the presence of acid gives rise to an alcohol. The second reaction that we're learning about is dehydration of alcohol, basically the loss of water, and this leads to the formation of an alkene. So it's just the opposite of the previous reaction, and this reaction is actually one of the chemical properties of alcohol. That was the synthesis, but this is the chemical property. So here you have an alcohol, it's reacting in the presence of acid, and on heating leads to the formation of an alkene. Right, previously it was alkene is reacting with water in the presence of acid to give us an alcohol. It's the opposite, right? So basically you put the mechanisms side by side, you'll actually notice there are a lot of similarities between the two. Here, first step is the formation of protonated alcohol. The last step in the synthesis of alcohol was basically the loss or the deprotonation to form an alcohol. Right, then we had the first step. The second step here is the formation of carbocation. There it was actually the first step, which was the formation of carbocation. So there are quite a bit of similarities between these two mechanisms. So let's start. First of all, you have the formation of protonated alcohol, and this is done because of the presence of the H plus group. So let's take an alcohol. In this case, we are taking ethanol. So this is ethanol. So CH3, CH2, OH. This is reacting with the H plus. So when it reacts with the H plus, the lone pair of electrons will come attack the hydrogen atom. And when it attacks the hydrogen atom, it itself is getting protonated, leading to the formation of a protonated alcohol. So here you have CH3, CH2, OH2. So the oxygen atom is getting a positive charge. Now what happens is this protonated alcohol will lose the water molecule, and this leads to the formation of a carbocation. And this step is actually a slow step. And so every reaction, whichever is the slower step, is considered the rate determining step. And because this is the slowest, this one will be considered as the rate determining step. Now, this is the protonated alcohol. What is going to happen? This bond is going to break. And since these electrons are moving to the oxygen atom, our carbon atom is getting a negative charge. So this is a slow step. Oh, one more thing. This is a fast step. Protonation is a fast one, but this loss of water to form carbocation is a slow step. So we are getting a carbocation. Now this carbocation has to get converted to an ethene. So let's take the carbocation first. Okay, we have the carbocation. Right. Now what happens is it loses this hydrogen atom. Now when this loses the hydrogen atom, bond shifts this way and you have a double bond between both the carbon atoms. And this leads to the formation of an ethene and a H plus. So what are we doing first? The protonated alcohol is formed. This is by the lone pair of electrons attacking the H plus. And this is the fast step. And the H plus, why is it present? It's because of the presence of an acid. It is done in the presence of an acid. And the next step, and in case of primary, we are actually using a strong acid like H2SO4. Next, what is happening is you have the formation of a carbocation. The carbocation is then going to formed by the loss of water, and this hydrogen is lost to lead to the formation of ethene. Right. So basically we are going from an alcohol to a protonated alcohol to a carbocation to an ethene. Let me just write it down. Alcohol is getting converted to a protonated alcohol okay, and this is then getting converted to a I'll just write it here. Wait. We're getting a carbocation. Okay, now this carbocation is getting converted to an alkene. And the first step is taken by the addition of addition of H plus. This conversion takes place by the removal of water minus H2O. Carbocation is also losing a H plus. Put these in boxes and you have the mechanism in just one line. Okay, so with that we're done with the dehydration of alcohols, that is the loss of water molecule. Alcohols undergo dehydration in the presence of acid to give us an alkene. Primary alcohols require a very strong condition, but secondary and tertiary alcohols require mild conditions for the conversion to form an alkene. The next reaction is again a dehydration of alcohol. But the thing is, alcohol in the presence of on reaction with H2SO4 at a specific temperature lead to the formation of an alkene, and another temperature lead to the formation of an ether. So this is applicable only to primary alcohols. Now let's first look at the reaction here. You have ethanol in the presence of, on reaction with H2SO4 rather, at 443 Kelvin, it leads to the formation of an alkene. So the previous mechanism that we all learned, that is the one which is going to get followed. But at 413 Kelvin, it is leading to the formation of an ether. Now, there is a difference in terms of mechanism. Okay, but I would suggest if you're doing all the mechanisms at one go, you might as well do it like parallel to each other because they have similarity in terms of the various steps. Now, the reason why primary alcohols alone follow this particular reaction is because secondary and tertiary alcohols actually require milder conditions for them to get converted to an alkene. So we are using only primary alcohols. So the first step is similar to what we studied in the previous mechanism. So ethanol is getting protonated in the presence of H+, and this leads to the formation of a protonated alcohol. So I'm just going to write CH3. See, I'm expanding this carbon atom structure. So this OH is going to get protonated by H+, and that happens because of the lone pair of electrons. And this leads to the formation of a protonated alcohol. Now, in the previous reaction, that is when the temperature is 443 Kelvin, this step would have led to the formation of a carbocation because of the loss of water molecule. But this reaction is taking place at a lower temperature, and there is another type of reaction taking place. The second step is the nucleophilic attack by another alcohol by elimination of water. So in this reaction, what is happening is the nucleophilic attack by another alcohol atom is taking place, whereas in the previous reaction we had just the loss of water directly to form a carbocation, right? And in that case we had the synthesis of an alkene, but here you have synthesizing an ether because this is one of the preparatory methods of ether. So CH3, let's take the protonated alcohol. In the previous reaction, we would have just removed the OH2 to lead to the formation of a carbocation. In this reaction, however, you have CH3, another molecule of an alcohol, of the alcohol rather. The lone pair of electrons on the OH is going to come attack this carbon atom, and this leads to the loss of the water molecule. So OH2 is going to get kicked out. Now, so here what is happening? CH3, CH2, OH plus CH2, CH3. Okay, now what happens plus water? Because that's what was removed in the previous case. Now what will happen is, this is called the oxonium ion. Now this oxonium ion will kick this hydrogen out to form an ether, right? So CH3, CH2, O, CH2, CH3, and you have a H also to attach to the oxygen atom. Oh, that's not visible. Okay. You have the H attached to the oxygen atom, and that's why it has a positive charge. It has 3 bonds, right? So it prefers 2 bonds, so it basically, there's a bond break between the oxygen atom and the hydrogen atom. And what happens? Since the electrons of this bond are shifting to the oxygen, hydrogen is kicked out as a H+. So that's a proton. CH3, CH2, O, CH2, CH3 plus H plus. So in this reaction, first of all, the temperature is very important. This is synthesis of ether. So first step, the ethanol, the alcohol, is getting protonated. It's similar to what we studied for dehydration of alcohol to form an alkene. Next, there's a nucleophilic attack by another alcohol atom and this leads to the elimination of water. When there is an elimination of water, this OH2 is getting removed completely, and the lone pair of electrons are basically, there is a new bond between this carbon atom and this oxygen atom. So that is this one. Okay, and the carbon is the oxygen atom is already bound to a carbon and a hydrogen atom. Then what happens is there is a removal of this hydrogen because, oh, there is oxygen atom requires, is always going to have only 2 bonds. So we are basically removing this as a H plus. With that, we're done with the dehydration of alcohol. To sum this up, the mechanism of 3 reactions that we've learned till now is basically either first one was an alkene to an alcohol, the second was an alcohol to alkene. Now in this case, it is an alcohol to an ether. Okay, so all of these are quite related to each other, and I would suggest that you try and do it side by side, so you'll be able to, you don't have to memorize a lot, you can understand and do it. Okay, with that, we're done with the dehydration of alcohol to form an ether. This is the last reaction, or rather the last mechanism we'll be learning about in this chapter. Cleavage of CO bond in ethers. So ethers are compounds which have ROR. That is, there is an oxygen which is bound to 2 different or 2 similar, depends upon the ether we are talking about, alkyl groups. Now the ether as such is considered as one of the most stable functional groups, and it generally does not undergo a chemical reaction, and it requires a drastic conditions for a reaction to take place. So when you have an ether, let's take ROR. Okay, it's a symmetrical ether, which means this alkyl group is and this one are the same. So it reacts to give us 2 alkyl halides. Now what happens is it reacts with a hydrogen halide HX to give us an alkyl halide and an alcohol. Okay, now this alcohol will further undergo a reaction with the hydrogen halide to give us another molecule of the alkyl halide and then molecule of water. So an ether, and this is in extreme conditions. So an ether is undergoing reaction with a hydrogen halide to give us an alkyl halide and alcohol, which the alcohol is again undergoing a reaction with the hydrogen halide to give us an alkyl halide and water. Now let's look at the mechanism of this particular reaction. So the first step would be the protonation. So first step, you have protonation of ether. So you have here we have an unsymmetrical ether. Okay, okay, first let's look at the one which is symmetrical. So ROR plus HX. Right, so what will happen, the lone pair of electrons will come attack this hydrogen to lead to the formation of an ROH R with a positive charge. Now, and you will also have a formation of an iodide ion. Now this iodide ion will attack the R group, and since these two are basically similar R groups or the same alkyl groups, it will attack either of these two. So you have the attack of the iodine or the iodide ion on the, so the iodide ion will attack, let's take this R group. So it will attack this R group, and this will lead to the formation of a ROH, okay, plus an RI. Now this ROH is further going to undergo a reaction with the HX. So what will happen? The lone pair of electrons on the this should have been X. Is undergoing a reaction with HX, okay, to give us ROH plus, because it's bound to 2 different hydrogen atoms, plus I minus. Now what will happen is this will attack the carbon atom of the alkyl group for us to get Ri plus H2O. Rx plus H2O. So this is the basic idea behind the mechanism. Okay, so first you have the protonation taking place, and then what will happen is this X minus is attacking one of the alkyl groups, and because both the alkyl groups are basically the same, you have this is symmetrical ether. We are getting an ROH plus RX. The ROH is again going to undergo a chemical reaction for us to get the other molecule of RX. Now this is the basic reaction when you have a symmetrical ether. Now when you have an unsymmetrical ether, the same reaction is going to take place. So I'm just going to erase this here. So that was for a symmetrical ether. Now let's take an unsymmetrical ether. Okay, now this means ROR dash. Okay, now ROR dash implies, so ROR dash, it's an unsymmetrical ether, is reacting with HX to give us RX plus ROH. Okay, now remember, the order of reactivity in case of the hydrogen halide is going to be hydrogen iodide is more reactive than hydrogen chloride, hydrogen bromide, which is more reactive than hydrogen chloride. Okay, now when you have this particular case, we need, first of all, the reaction takes place at a high concentration of the hydrogen halide and also at a high temperature. Now let's look at the mechanism. We are taking the example of an ethyl-methyl ether, which is CH3O CH2 CH3. So you have an ethyl group, you have a methyl group in this ether. Now similar to the first case, the first step over here is going to be protonation of the ether. Okay, now CH3O CH2 CH3, and we are assuming this reaction is taking place with HI. Now the lone pair of electrons on the oxygen atom is going to come attack this, and what will happen is it will basically pull the hydrogen away from the iodine. Okay, and this leads to the formation of a protonated ether. So there's going to be a OH plus and CH2 CH3 plus I minus. Now this is a very crucial step. Now in the previous case, it didn't matter which alkyl group was attacked by the iodine, right? It didn't really matter. But in this case, it actually matters which alkyl group is going to get attacked by the iodine, because here you have a CH3 which is a methyl, whereas here it's an ethyl group. Now what happens is the iodide is going to act as a good nucleophile. Okay, and when it acts as a good nucleophile, it is going to attack the least substituted carbon atom, and in this case this carbon is least substituted. This has another alkyl group, but this just has 3 hydrogen atoms, so this is the least substituted alkyl group of the oxonium ion. Okay, so here you have a CH3O CH2 CH3, okay, and this is having a positive charge. Now the iodide ion is going to attack the least substituted, and in this case it's the methyl group. Oh, you're not able to see. Yeah, the least substituted methyl group, by basically it's going to get transferred like this, and what will happen? This bond will start to break. As this bond is starting to form, this bond is going to start to break. And this leads to this particular complex. You remember the transition state by the SN2? It's similar to what we see there. So here you have a CH3, okay, you have a bond breakage between the oxygen and the carbon. That's why, and this bond is going to be a solid bond. and this bond is a CH2 CH3. Now in here what is happening is the alcohol molecule is displaced by the SN2 mechanism. So the SN2 mechanism is taking place. So we have the formation of an alcohol, that is CH2CH2OH and a CH3I. So we are getting a CH3I alkyl halide plus an ethanol. Now, since this reaction is taking place in extreme concentration, at a high concentration of the of the hydrogen halide, and at a high temperature, this alcohol is going to also get converted to an alkyl halide. Now, let's look at that part of the reaction. So, you have a CH3, CH2OH plus HX or HI, sorry. So the lone pair of electrons on the alcohol is going to come attack the hydrogen atom. Now this will come attack over here, this will get shifted there. So the I atom, the iodine, is going to get converted to an iodide ion. So CH2OH2 plus charge plus an I minus. Now again what is going to happen? The I minus will come attack this carbon atom and kick the water molecule out. So here you have, and this is going to get removed, and here you have the formation of an alkyl halide. Sorry, alkyl halide plus water. So first step, what is happening? First of all, we're considering an unsymmetrical an ether. What is happening is, first you have the protonation of the ether taking place. Then you have the iodide is going to act as a nucleophile and it is going to attack the least substituted alkyl group of the ether, and that in turn is going to lead to the formation of an alkyl halide and an alcohol. And then you have the alcohol getting converted to the ether by the nucleophilic attack, converted to an alkyl halide by the nucleophilic attack of the iodide ion. The next one we are going to be talking about is the nature of the alkyl group is obviously decided. So the primary and secondary alkyl group and the lower alkyl groups are forming alkyl iodides. So the alkyl halide as well as an alcohol are the products formed in this particular reaction. The lower substituted alkyl group is forming an alkyl halide. The more substituted one is forming an alcohol. Okay, so the primary and the secondary, right, they form an alkyl halide. Now we have to consider a tertiary group. Now, so we have a tertiary alkyl group attached to the ether. Okay, and in this case, there is something very unique happening. Let's consider this reaction. CH3, C, CH3, CH3. This is a tertiary alkyl group and another CH3. So this oxygen atom is bound to two different alkyl groups. So it's an unsymmetrical ether, right? So here you have this carbon atom is a tertiary and this is a primary alkyl group. Now when this reacts with HI, now in the previous case we discussed that lower or primary and secondary, the lesser substituted carbon atom is going to give us an alkyl halide. But in this case, the more substituted one, that is this carbon atom, is giving us an alkyl halide, and this is because it follows the SN1 mechanism. In this case it was the SN2 mechanism. In this case it's an SN1 mechanism. So here you have an alkyl halide formed from the tertiary alkyl group, whereas the primary is giving us an alcohol. So this is by the SN2 mechanism. This is by the SN1 mechanism. I hope you know that by now. So let's look at the mechanism. So first step is obviously going to be the protonation of the alcohol, and this leads to the formation, protonation of the ether, and this leads to the formation of the our oxonium ion. So CH3 is getting protonated, okay, OCH3. This is going to get protonated by the similar reaction up there to give us a CH3, CH3, OH plus CH3. Now this is the oxonium ion which is formed. Now what happens is there is a slow conversion. By the loss of this bond is going to break. Okay, and this gives us a very stable tertiary carbocation. In this case, you had a transition state forming, right? This because it's an SN2, whereas this is going to be an SN1. So this OH, CH3OH is getting kicked out. Okay, and this leads to the formation of an tertiary carbocation, and this is a slow step. This is a slow step, and so you get a CH3, CH3, and this carbon atom has a positive charge plus CH3OH. Now, what happens is this carbocation which is formed is going to undergo a reaction with I minus, which is already present. So CH, let's just write down the carbocation first. And since it has 3 alkyl groups attached to it, it's quite stable too. So it is going to react with the I minus. Okay, and this is again going to follow. This is also going to be slow. Oh, sorry, this is fast. I'm so sorry. This is a fast step. And here you have the formation of an alkyl halide. Now in the previous case, the reason we had the lesser substituted one as the forming the alkyl halide, whereas the more substituted one formed the alcohol, right? And that is because it followed the SN2 mechanism. This, in case of tertiary, it is following the SN1 mechanism, and because of that, the tertiary group is going to form the alkyl halide, and that is because the carbocation, the tertiary carbocation, is more stable than primary or secondary carbocation. Now, we also need to consider the presence of, let's take for example anisole. This is anisole, which is benzene with an OCH3. This is also an ether. Okay, now when we consider anisole, it leads to the formation of the O plus. So this will form the OH plus. Okay, this will be the intermediate form. Now the CH3, okay, is less substituted than this carbon atom is attached to other carbon atoms. So the CH3 is actually going to form a CH3I if we are reacting with HIA, and there is a formation of phenol because you have the OH. Now CH3 is getting removed and you have the formation of a CH3I and a phenol. Now this phenol is not going to further undergo reaction like this alcohol. Like this happened, it won't happen in case of a phenol because it is stable towards the reactions towards hydrogen halides. And with that, we're done with the cleavage of CO bond in ethers. So remember, when you're talking about an unsymmetrical ether, first of all, in case of a symmetrical ether, all of this does not, we don't talk about, okay, which more substituted carbon or it's a less substituted, because both of them are basically the same alkyl group, or they're similar. Whereas in case of unsymmetrical ether, we start questioning about the substituent, number of substituents attached to the alkyl, or rather the carbon atom. In case of a secondary or a primary alkyl group, it is going to follow the SN2 mechanism, and this is leading to the formation of an alcohol by the more substituted group and an alkyl halide by the less substituted group. The alcohol is further undergoing reaction to form the alkyl halide. But in case of a tertiary group, you have the formation of a carbocation, and this reaction is basically going to be through the SN2 process, and this leads to the fast reaction. This is the formation of a carbocation. Did I say SN2? Sorry, it's going to take place through an SN1 process and leads to the formation of a carbocation. And since it's a tertiary carbocations are quite more stable than primary or secondary. This was an SN2 mechanism. Transition state SN1, you have the formation of an carbocation, and this in turn is going to get attacked by the iodine. And so here, in case of tertiary, we expect the CH3 to form an alkyl halide, but this to form an alcohol, but it's actually the other way around because of the formation of a carbocation, because this reaction is taking place through the SN1 process. In case of anisole, you have an aryl group, that is benzene, and you have a CH3. Now, the iodide ion can attack either this carbon atom or this carbon atom. Obviously, it won't attack this one because it's more substituted and more stable. And OH, this bond is actually quite more strong, or rather more stronger than this bond. Okay, this is because of the resonance and all the various structures that we form, and because of that, this bond is actually stronger, and it's shorter than a single bond. So because of that, we have the CH3 getting removed out as the alkyl halide, and this forming a phenol, and phenol will not undergo further reaction with hydrogen iodide to form an alkyl halide. With that, we're done with the cleavage of CO bond in ethers. So we learned about 4 reactions in this video. We started with learning about the conversion of an alkene to an alcohol by the addition reaction of H2O in the presence of an acid. Then we moved on to learn about the dehydration of alcohol to form an alkene. Next, we studied about the dehydration of alcohols to form ethers. The difference between the two are the temperature. So at a higher temperature, alkene is formed. At a relatively lower temperature, an ether is formed. The last reaction we learned about is the cleavage of CO bond in ethers. And this is actually a single topic. We have a mechanism in that, but I thought it would be better if we could discuss the whole thing as one part. So with that, we're done with the various reaction mechanisms in the chapter alcohols, phenols and ethers. You can go through the chapter itself. There are notes also attached in the description, and you can also go through the chapter P block elements, which is a part of this playlist. With that, we're done with the chapter alcohols, phenols and ethers.